Great. Good afternoon, everyone. So welcome to another working group one invited talk. So this afternoon we have Professor Hala Skaf-Molli. So Hala Skaf-Molli is a full professor in computer science at Nantes University and leads the Distributed Data Management DDD research team at the Nantes Laboratory of Digital Science, LS2M. Her research focuses on large-scale knowledge graphs, federated knowledge graph systems, and neuro-symbolic approaches. She regularly publishes in leading international venues such as ESWC, ISWC, and ACM, the Web Conference. She has participated in numerous national and international research projects, coordinated the national ANR Decology project on Decentralized Knowledge Graph 2019 to 2024, and currently coordinates the ANR Safe KG projects on querying over secure federations of knowledge graph 2025 to 2029. Okay, Hala, welcome. The floor is yours. Thank you very much.
Thank you very much for the introduction. Thank you for the invitation. I am really happy to be with you today. So let's start. In this talk, does not work. In this talk, I will talk for you how we can make carrying large knowledge graph practical, such that we can use it in real-world application. In order to do that, we need completeness to avoid partial result. We need federation as data are decentralized. We need interactivity in order to explore large knowledge graph. And of course, today we need LLMs that we use more and more. In this talk, I will present the contribution of GDDT. I will not go in deep technical presentation. I will present for you motivation, problem, key ideas of the approach, and some experimental results. So let's start about completeness. Imagine I want to know all verified fact about French public university. I want to have correct and complete result. I don't want to have hallucination. So one way to do that is to go to carry a knowledge graph. In this example, I carry DBBD knowledge graph. It contains information about common knowledge about French university, such as number of students and the location of the university. So I can go to the public SPARQL endpoint of DBpedia, write this query, don't worry, trust me, it will give me everything about French university. So I can write this SPARQL query and execute it on knowledge graph of DBpedia. Knowledge graph DBpedia give me this number of results. So if we go and check what inside this result, we can see that we have information about location, number of students, associated laboratory with the university, and usually we have also information about famous people at the university, well-known people in the university. So that's good, but in fact, there are many existing knowledge graph that can answer my question. For instance, I can use Microsoft Knowledge Graph. It contains information about publication. I can use Wikidata and a large number of knowledge graph. In order to execute this query on this large number of knowledge graph, I need to use federation engine. Federation engine allow to carry remote knowledge graph without the need to copy data into a centralized server. So the data stay under the control of data provider, and the knowledge graph is a middleware between the user and the knowledge graph. So in this example, I use a federation of 4 knowledge graph, and I use the federated engine FedEx in my federation. What's good with the federation engine is can find the source and carry the source for you. It means when the federation, when I send my query, federation engine will decompose the query, send the query to relevant endpoint, and give me the answer. For me, it's transparent. As a user, I am happy with that. This is the story, but the reality, in fact, it's really different. In fact, when we use SPARQL endpoint and we use federation engine, we have many problems. With SPARQL endpoint, we have problem of completeness. With federation engine, we have problem of scalability. So when I go to execute my query in Wikidata, in fact, Wikidata will time out. My query will stop it after 60 seconds, sorry. And this is because of fair usage policies. It's normal to keep the server responsive. And if I try to execute the same query in DBpedia, my query will stop it because there are many results. So because of quota in number of results, the query is stopped also. So I cannot have complete result. I cannot use it in real application. Another problem is the scalability of federation engine. Here in this example, I have a federation of 200 shop. In this example, I use FedShop, a benchmark for testing scalability of SPARQL federation engine. I have 200 shop, and I try to find in this shop similar product in federation of this shop. And if I use the state-of-the-art federation query engine COSFED for 200 endpoint, after 1 hour, I have no result. So I stopped the execution of the engine. There is really a problem of scalability. So what we did of GDD team, we work on this problem. We work about how to provide online query service that ensure complete results. It's important for application to have complete result, else it's useless. And we work on this problem, how we can make federation engine scalable. And that's what I will try to answer this. I will try to answer these two questions. Let's start with the beginning. We worked in that to have really, we want to have ensure complete result for our SPARQL endpoint. In fact, why we have this problem timeout and to many that? In fact, federation engine, to preserve responsiveness, they define a quota in order, they provide only partial result in order to keep the server responsive. So, however, with this, we cannot really use it. So what we did, our question is, we want to deliver a responsive and a server that able to deliver complete results. So that's what the research question that we want to handle. What we propose the approach of continuation queries. The idea of continuation query is, okay, I have a server with timeout, no problem. So when the user sends the query, when the timeout reach it, for instance, 60 seconds, as in Wikidata, the query will be suspended and resumed and send for the user the partial result obtained during this time, and a continuation query that can compute missing result. Continuational query is like a normal SPARQL query we have with offset and bound. We use only SPARQL operator to generate this continuation query. And here, the user can send this continuation query to generate another continuation query. And one continuation queries lead to another one until we get all results. So with continuation queries, we are able to have completeness. In our paper published last year, we defined a formal framework to allow to prove important property for continuation query, correctness of the result, termination, continuation query, bounded size, and we prove this property for core SPARQL. So we have not full SPARQL, we have only this part of SPARQL operator. I will show you some experimental study about this continuation query to show you that really it works and we don't have a lot of our head. To do that, we take Wikidata benchmark and we selected queries that has more 60-second execution time and less than 5 minutes, and it's more than 60 seconds because it's the time quota of existing SPARQL endpoint. And we run this query with different shape of run execution and experimentation with different shape of SPARQL query. We try with existing engine. Here we'll use BlazeGraph and Angina and Passage without any quota. It's a touche, and Passage with 16 seconds of cutoff time. This allows us to measure the overhead of the continuation query. Here, Passage run as a normal SPARQL query without any continuation queries. So we run this experience with one CPU, and as you can see, if we compare the total execution time for all workload of the query, and we find that the difference in execution time between Passage with quota and Passage without quota is less than 2 minutes. This means the marginal overhead of continuation query there's a marginal overhead of continuation queries, so it works. And if we compare with BlazeGraph, it was surprising for us to see that we have better execution times than BlazeGraph. Remember that BlazeGraph is the server behind Wikidata. So we have better execution time, and this is because we have better join ordering, and for that, continuation query with Passage deliver high performance. When we try with 4 CPU, BlazeGraph is better than us, and this is normal because BlazeGraph use intra-query parallelization, and it's good for performance. This means with Passage we can go further with optimization. So why I present you continuation query? Because for me, I think it's very important to have this kind of contribution, because in the state of the art, we have a lot of work dealing with this problem of incomplete results, with completeness. But continuation query are the only available solutions that use pure SPARQL. This means I can implement it immediately in existing RDF engine in current SPARQL endpoint and SPARQL server. And that's what we do. We do it on BlazeGraph. So it works and we have good performance. There's an implementation of this continuation query. We have a server that implements core SPARQL. And as we don't have all the operator of SPARQL, we use Passage Communicate to execute full SPARQL. What is interesting with, if you want to try it, it's available online. You can see through this address, you can access our server. What is interesting in server, you have Passage and Passage with continuous query, and you have the Wikidata SPARQL endpoint. So it means in the same server, we can run both approach. So as a user, I can start executing on Wikidata if the query timeout, so I can switch to Passage in order to have complete result of my query. Now, good, we have solved the problem of completeness. No problem, no more fire on completeness, but we have still problem with this federation engine. So let's go and try to see what the GDD team do to solve this problem. As I told you at the beginning, federation engine do not scale for 200 endpoint, and this is not good for practical application. So, in fact, we write a query plan, we handcrafted query plan, and we see that wow, it's possible to execute this complex query on 200 endpoint and really quickly. So why existing federation engine are unable to execute this query? So in fact, I will show you our FedUp, our federated query engine that able to execute define good planes and have good execution time, acceptable execution time. So the problem is, if we look at the state-of-the-art federation query engine, they provide what we call join over union query plan, logical plan. With handcrafted plan, we have what we call union over join. So it seemed to be a good idea to have this plan. The question is, why there is good plan, and why existing federation engine cannot find them? In fact, that because federation query engine only searched and build what we call joint over union query plans. So the union over join query plans are not in the search space of existing query engine. So to explain, I will try to illustrate the difference between the two query plans during using this example, sample example. Imagine I have federation of four SPARQL endpoint, D1, D2, 3, and 4. And this is what the data in the represented in my federation. And I want to look for musical bands located in Germany. This is a sample SPARQL query, federated query. So I can write this query. And I try to find, as we can see, there are relevant sources for each triple pattern, where we can, this means this source can have answer for this triple pattern. And when we build union, and when we execute this query, we find that we have only two results. It means we have only combination for only combinations that can give results. So if I explain it in better, I will say, if we take existing federated query engine, it will build this kind of logical plane. So if we see this one, this means there will be 8 calls to endpoint. When we have this number of endpoint, each time we have endpoint, we have intermediate results come back to federated query engine and generate a lot of transfer and need more time to execute the query. If we look to union over join query plan, we have only 4. And however, this one is not in the search of space of existing federation engine. As we can see here, we can have 2 combinations that provide result. We don't have many combinations that this means this plan will produce a lot of combination of data sources that will not produce result. With union of a join, we have we have more exclusive group, so we eliminate group that do not produce result. So in order to build this logical plane, we have the idea that, okay, we can evaluate the query on the federation and track the provenance. Seems good, because we have only the combinations that produce result. And after that, we will construct a query union of union query plans that allow to find, we will return union of union plans that good for executing the query. However, if I want to, it's not a good idea to execute the query, because to find the plan, I need to execute the query, and it's useless. The idea that we find, we said, oh, instead of run the algorithm on the federation, we will execute it on a summary of federation. And the question is, which summary and how to build it? We comes with this idea to use quotient summary. And quotient summary, it's homomorphism of the original graph. Here is my original graph, and here is the summary. And I use this function in order to produce this quotient summary. The idea here, For each node, I will keep only the authority. And when I have a label or constant, I will project it on any. And with this, in this example, the size of the federation is similar to the size of summary graph, but in a real situation, you will see in the experimental study, it's really small. What is good with these question summaries is we can build them using a SPARQL query, and we will only transfer the size of summary, will not transfer intermediate results that useful, so only the size of summary, which is small. And what is good with this question summary is that if we have no result on the summary, so we are sure not to have result on federation, but if we have result on the summary, maybe we have results on the federation. So what we did, we have this original federated query. We use the summary function in order to transform this query we rewrite the query to be executed on the summary. So if we execute in summary without no result, we stop. We don't need to execute it on the federation. If we have results, so go and execute it on the federation. And we conducted experimental study with two benchmark, larger depth benchmark. It's not so challenging. It has only 14 SPARQL endpoint. We experimented with FetchUp, which is more challenging. We can go from 20 endpoint to 200 endpoint, and it's in this table I present you the size of summary. In fact, if we can look, the size of summary FedUp, it's really very tiny, small compared with the size of the federation. So even with 200 SPARQL endpoint, 200 knowledge graph, we have a small summary. And to see if this work good, we run experimentation to see execution time for larger depth benchmark. In the x-axis, we have the query. In the y, we have the execution time in logarithmic scale, and this is the timeout we set. So what I want you to see FedUp in green, COSFED, which is the set of the art, and in yellow, our handcrafted query plan. As you can see in this, there is really, FedUp does not perform other engine. It's normal because, in fact, most of the query are relevant to one triple pattern, so there is no optimization to find exclusive group. So in this case, join offer union or union offer join are the same, no matter. But when we execute on more challenging FetchUp, on more challenging benchmark such as FetchUp, with 20 SPARQL endpoint and with 200, we can see that FedUp is really performant. It outperform other engine from 1 to 3 order of magnitude, which is very, very good. And for most of the query, FedUp it's really close to RSA, and scale well for 200 endpoint. And for some query here, we are really far from the reference, the handcrafted query plan. This is because of joint ordering and optimization problem. So we did an experimentation and demonstration for this our FedUp. We have an application called Fed Discount. It allowed to make shopping on a federation of 200 shop. Here an example with 100 shop. I want to find all information about this product. So it's, in fact, this will generate a federated query, and this is the answer for this query. And here, as at right, you can see the query execution plan and its color corresponding to a SPARQL endpoint. So if you are interested, you can see the team. With that, we are happy. We don't have no fire for SPARQL endpoint and no fire on the federation engine. Good. Now I want to switch to show you what we did on interactive query processing and approximate query processing. Because up until now, I present query processing that produce complete results. But in some use case, we don't need to have this complete result. We can have a sampling of the result. I will present for you quickly 3 contributions on how to use sampling with random walks in different use cases. The first contribution is Regina. In many applications such as computing large-scale statistics, embedding, approximate query processing, summary, and exploratory queries, we don't need to have a complete result. So we can have approximate query execution. So what we did, we make an extension to Apache Gina, we call it Regina, and this extension supports sampling-based approximate query processing. Regina is able to deliver partial result, and the cardinality of this estimation of the result in Bayes-Coutts fashion. Here, I present you an example of this query that time out on Wikidata. And this query gives this number of result, 25 billion. And with Wikidata, we don't have any answer. With Regina, we can have sampling of result. Each time with the sampling, we have the estimated number of the result. And if we continue to execute the execution, we will have all the result, and we will be not far from the good estimation of the cardinality of the result. And when we have more sampling, and this was demonstrated in International Semantic Web Conference, and you have every information are available in the paper. We have another contribution about sampling. It's crowd. With Regina, we don't handle the problem of count distinct because it's really hard to handle this problem because you have to remember what you see before. And this kind of query is interesting because I can, for instance, have the query like how many women head cities in Europe. This kind of query time out on Wikidata. But what the main idea that we develop here that instead of when we sample a query, we sample its frequency at the same time. And as frequency is less than the number of different values, so it's efficient. And we demonstrated in the paper that with frequency, we can estimate the number of distinct value with a good precision, as you can see here. Compared with existing estimator, crowd is outperform other, and it's not far from the expected real value of the number of count distinct for this query in the benchmark. Last contribution about sampling, it's Fro. Fro, it's a federated query engine based on sampling. And in this scenario, we show how we can use it for auto-compilation of federated query. It's really hard to write a federated query for a federation of 200 endpoint, 200 SPARQL knowledge graph. So what here, when the user writes the query, he can click to find a possible compilation for the query. And the compilation is, and the system will suggest in an interactive way a proposal of what possible value. And to do that, the system produce a auto-compilation query that retrieve suggestion for the user. If we execute this query with FedUp, it's too long for interactive exploration. When we execute it with sampling, it's really too fast, and it's really interesting to use sampling for auto-compilation suggestion. And we implemented that in using FedUp for source selection, as we are in federation, and we use this Hequin query execution engine for execution. We implemented overloaded the operator, and we implemented sampling. Now I will go to last four elements that we need for having a real application running with this SPARQL technology. So the last one, we cannot speak today without saying something about LLM and knowledge graphs. So let's go. Hello, I will present you two contributions quickly. The first one, LLM for schema. The idea here, if we go to web page, only 67% of web page have structured data, and not all do not have structured data. And some of page have this structured data using schema.org. And we want to complete this web page to have this structured data because it could be interesting for search engine. It's good to have this semantic annotation. And yes, we can use LLM to generate, but the question is how we can check, how we can validate the quality of generated markup, generated annotation. Our key idea was, it's okay, we don't have ground truth, but we will replace this with fair competition between LLM and human. The main idea is we will give to the same page, web page, to a human and to a LLM, and we see who will generate the most correct and complete markup, and the winners will be the one who generates this one. It's like a competition, like a game. So to do that, we develop a pipeline. I will explain quickly this pipeline because we want to make fair comparison. For that, we have eliminate incorrect and annotation. We give to the human and to the LLM the same web page and with typed coming from schema.org. We ask a human to add annotation and LLM. And after that, we check for validity to see if they are correct with respect to the syntax of schema.org, if they respect shekel constraint. We go to, after that, we keep those who are validated, and we go to check faculty to check if the annotation are grounded in the text. And if not grounded in the text, it could be kind of a hallucination. So we eliminate it, and we keep all this grounded. And after that, we go to the first check was to see compliance. That does did the annotation are compliant with schema.org type and definition. So we implemented this as a LLM agent to make this validation. And after that, we defined a metric to check who is winner. The idea of the metric, we merge annotation coming from human and from LLM, and we measure the contribution at each one. The one who has the most contribution is the winner. We conducted experimentation with the different LLM, and the winner was GPT-4. It produces better annotation than human. The last contribution, I want to speak about SPARQL LLM. It's what was the motivation between this SPARQL LLM? In fact, we start with this question. We want to find cultural event available in Europe capitals. Okay, if I want to answer this question using SPARQL query, I can go to Wikidata to find capitals of Europe. It's easy. I can write this query. But if I want to know information about events are not in knowledge graph, they are in external web page. And the question that we ask, we want to answer this question using one SPARQL query. How we can carry these heterogeneous data sources in one SPARQL query. Our idea was to use user-defined function. And for here, you can see a kind of user-defined functions that allow to carry remote server heterogeneous data. And what is the most important idea in this contribution is that we can, during execution SPARQL query, we can generate dynamically named graph. Here, this knowledge graph, we can use it during the query. This is new, does not exist really in SPARQL. this is very interesting. And what is good to do that in SPARQL query, because with this, you don't need to transfer about a lot of intermediate results. You transfer only data necessary to answer this query. With this, I finished to represent the contribution of GDDT. For completeness, we have contribution about continuous query. I think this continuous query resolve a real problem, and it's important to have complete result if we want to use SPARQL endpoint in real application. And what is interesting, we can implement it in any current engine because they are just standard SPARQL query. What we are doing now, we are working to extend our server, because now in our server implement only core SPARQL. We want to go to full SPARQL. We are working now on integrating the property path, because it's most important. It's very interesting to have important to have all the operator in the server, because it's more efficient. You don't have a lot of data transfer between the client server, and it's interesting. Another thing, it's yes, we proposed a federated query engine that can scale until up to 200 SPARQL endpoint. And thanks to
Sorry, we're running a little bit over time. Maybe we can
sorry.
finish quicker.
Yeah.
Sorry.
I know I finished. The last thing I want to say that we did a lot of work for the public SPARQL endpoint, and we have to go now for working with secure and policy aware federated with LLM and query federation. That there are national projects I coordinate on this topic. And last, I want to thank all people from GDD team who contributed for this work. I thank you for your attention. I am sorry for that time. I was very happy to present, so I am ready for a question.